Hello, my name is Patrick Cook, and this is my final project for my image processing and computer vision course. The title of my project is Object Tracking Evaluation for Intelligent Machine Design Lab. First, I want to start off with what inspired me to do this project. Here at the University of Florida, we have a class called Intelligent Machine Design Lab. It's a one-semester course offered to undergraduates and graduates. And basically, it's an opportunity to build and design an autonomous robot. In the class, they give you pretty much free reign as to what you do for your project. They just require that you have 4 different sensors, and they want this to include proximity detectors and bump sensors so you can do obstacle avoidance. And then they just let you pick whatever you want. So I saw this as the perfect opportunity to do an object tracking project, because that was what I found most interesting about this class. Now, for my robot, basically this is what I have envisioned what I would like to do for my project, and this is what my project is, my paper is based on, or my project for this class is based on. Basically, I was thinking I want a robot that can track an object and follow it around, and then if I have time, I can implement some kind of interaction with the object it's tracking. But for the structure of the robot, this is what I was thinking. Use tank treads for mobility. That way that you're not moving too fast and you don't have to worry about jerky motion. And also it allows it to move over a variety of terrain so that it can track things that go over obstacles and that stuff. At least that's what I'm thinking. I would like to keep it to a single camera because stereoscopic vision, it can get complicated, and I don't want that to take up my entire project. I'd rather work on the object tracking part. So I'll rely on a different sensor to do depth information and that kind of stuff. For acquiring an object, I would like the robot to look for a laser pointer on an object, ideally. I think that'd be really cool to have a robot that does laser designation, and then once a object has been selected, it will follow and interact with the tracked object, as I mentioned before. Alright, so now that I've walked you through this ideal robot, you're probably wondering, why don't you just do that in IMDL, or Intelligent Machine Design Lab? Why are we talking about it now? Basically, why I brought it up is because I'm not sure what tracking algorithm would work best for a robot of this type that moves on the ground and tracks objects of different shapes and sizes that they don't know ahead of time. So I figured that this would be a great opportunity, the project for this class, to explore object tracking algorithms and how they apply to this application that I have in mind. Now, before we get into the specific algorithms, I'm going to give a brief overview on what is object tracking, and that's basically when you project the trajectory of an object through the frames of a video. Now, it doesn't sound too terribly complicated, but when you start to break it down and actually work on it, it's actually a pretty tough problem. And it also has a lot of applications. It can be used to improve human-computer interfaces, like if you have a computer that's, that a human needs to interact with, you can keep track of their eyes and see where they're looking to help them get to what they need to know. You can also be used in navigation, and that's obviously what I'm planning on using it for, is for navigation and surveillance. That's a similar kind of application that's also kind of prevalent for what I want my robot to do. I want it to follow and track a person or an object through a scene. And when it comes down to it, object tracking requires 3 things. It requires a way to represent the objects you want to track, it requires a way to detect these objects you want to track, and then you have to decide which features in the images you're going to use to track this object. Now, when it comes to object representation, there's a few ways you can do this. You can just represent an object by a point, like at its center, as in A here, or you can represent it as a group of points, like in B. You can also use simple geometric shapes, such as a rectangular ellipse, seen in C and D. E is a more complex combination of simple geometric shapes. It basically is building kind of a segmented body, so you can deal with articulation and the different kinds of movement that come from that. Now the more complex representations gets where you're tracking like the outline and the contour of the shape, if you will. And that's what G and H represent. G is a contour that's represented by points, and H is representing the contour by the entire edge. From this edge, you can actually derive like a skeleton by doing a transformation, and that's what you see in F, and that's another way to represent an object. And then the last typical way you can represent an object is through its entire shape. You take the outline and everything within it, and that's what we call a silhouette, and that's what I represents. And these are all the different ways you can represent the shape of an object. Now if you want to represent appearance, there's two main ways you can do that. Basically, you can have a template or multiple templates that just have like color information in the shape. Like for the rectangle, you just store all of the color information from that rectangle, and that'll be your template. Or you can use like a histogram and keep track of the probabilities of colors in it, and that's usually typically used like with ellipses. You have an ellipse and you use a histogram. You keep a histogram of all the color distributions within the ellipse area. And once you have an object representation, you can perform object detection. And again, there's a few different ways you can do this. There's point detectors, which analyze an image and look for points within the image that are basically kind of an expressive texture. They're considered important points. They're typically not that basically you can still detect them regardless of the lighting or other factors, but basically it depends on the detector as to how it determines what points are important in an image. Another form of object detection is background subtraction. This is typically, actually it's required use of, you have to use a stationary camera because the background has to be stationary for you to do this. But basically the concept is you keep a model of the background from previous frames of the video, and you store it, and then in subsequent frames you subtract that background, and what you got left is the moving objects in the image, and that makes it a lot easier to find objects because you've already subtracted out everything that's potentially, or that isn't an object in the image. Two other ways of doing object detection is just doing image segmentation, which is kind of like background subtraction, except you're trying to get it so that you segment each object into its own segment, and then the background can be its own segment, or it may not. It might have separate segments, or depending on the algorithm or the detector. And then the last kind of object detection mechanism you can use is you can train classifiers using like machine learning techniques. Alright, so now we have a method. We have different methods of object detection. We have different methods of object representation. How exactly are we going to do the tracking? And basically the tracking is dependent on those two other things, the representation and the detection. There's three major classes of object trackers. There's point trackers, kernel trackers, and silhouette trackers. Point trackers, obviously, they use points as their representation, and they use point detectors most likely for their method of tracking. The algorithms can be deterministic or probabilistic, but regardless of that, usually these point trackers, since we're not taking into account the entire object, we're just picking select points out of it, they're usually typically better used for smaller objects that can be represented by a single point or a small set of points. Now on the other hand, on the other far side, we have the silhouette tracking, which basically takes into account the entire object shape. It keeps an entire outline, or even more, it keeps track of the entire shape and appearance of the body. These tend to be more complex, and in a robot, we're looking for real-time requirements. We can't be doing all these calculations. So in the middle ground, we have these kernel tracking algorithms, which take into account that you keep a template, which is usually a rectangular region that you look for in subsequent frames, and they look in the ballpark of where the object was previously for where it is next. Some algorithms try and do this smartly, other ones try and do brute force, but anyways, kernel tracking algorithms are the ones I focused on for my evaluation because they combined a lower computational cost with or they don't combine, they have a lower computational cost, but they're still able to represent a large variety of objects, and that's what I'm expecting to need for my robot. Now, in order to do my evaluation, I made use of the video verification of identity tracker testbed. It's an open source software that some researchers made to basically visualize object tracking algorithms and how effective they are and how accurate they are. They implemented it using OpenCV from Intel and the C++ language, and they're also nice enough to include some object tracking algorithms in this testbed along with some data sets. Now, these data sets are all aerial footage, so it's not exactly what my expected robot will have, but it does present some of the same problems, like a moving background because your camera is moving, similar objects, occlusion. It's pretty much a tougher problem, so if these tracking algorithms perform efficiently and accurately on these test sets, then I'm sure that they will do equally well on the easier data feeds that I expect from my robot to see. Here's a quick overview of the algorithms I decided to evaluate. Remember, they are all template-based kernel tracking algorithms. The mean shift algorithm uses an elliptical template representation. It has a histogram associated with it, so it's a probabilistic algorithm. It uses a gradient-based neighborhood search in order to reduce the amount of work it does in tracking objects between frames, and it's included in the Vivid testbed. We also have the variance ratio algorithm, which is basically an extension of mean shift, except the only difference here is that the feature set can actually change during execution in order to better facilitate a track. So it actually actively looks to see, is this feature set the one I should be tracking, and if not, it'll switch to a different feature set. This is also included in the Vivid testbed, and I should also point out that both of these algorithms use the color as their feature tracking set, and CFlow as well. And CFlow is the third algorithm I evaluated. It uses a rectangular template instead of an elliptical template, and basically can be considered an extension of the sum of absolute differences algorithm. Where it extends it is it uses these differences as an input into a Gaussian function before the absolute differences are accumulated. What this does is it ends up having a more poignant, a stronger response for close matches and a way weaker response for farther away matches. And the farther away it gets, the response in this Gaussian will be lower and lower. The CFlow algorithm is actually more brute force. It doesn't try and intelligently search the nearby area of the last object position. It just searches all possible frames in that neighborhood area, but the reduced computation costs with this CFlow computation, because the Gaussian is implemented as a lookup, it's pretty fast. It can do this brute force neighborhood search, and that also makes it kind of more robust in the fact that the gradient might not lead directly to the next object position. Now, this is the one I actually tried to implement and add to Vivid. So now that I've introduced the algorithms, I'll actually show you how they ran on a sample dataset from the Vivid testbed, and then I will discuss the relative performance of each of the algorithms, and that'll be the end of my video. For our first test run, we're going to use the mean shift algorithm. Let's set it up right here, and let's see what happens. As you can see, as it rounds the first turn, the tracker is doing a pretty good job. It's bouncing around a bit on the object, but it's still staying on it pretty well. Now the car is passing another object of the same type, and this tracker actually has no issues with it. It doesn't jump around to the object. That means it's pretty robust against multiple objects of the same characteristics, of the same appearance, which is good. This test run will be using the variance ratio algorithm mentioned in the paper. Let's get it set up, and let's see how it does. It handles the car in the turn pretty well. And we've totally lost track. It appears that as the car entered an area that looked a lot like the car, the street behind the car looks a lot like it. It caused the tracker to lose its track. Apparently, the features switching involved in the variance ratio actually did something that didn't really help the algorithm. It kind of made it worse. Okay, this is going to be the test run with the C-flow algorithm. Let's go ahead and check it off right here. Now you'll notice as the car comes around the turn, the tracker picks it up pretty well. It falls behind the vehicle a little bit. And as we move down the roadway, we still have a pretty good lock, but it's not going to hold. You'll see as it passes the other silver car, it's going to jump to it, resulting in a bad track. And as the car we're meant to track is moving along the road and never really catches up, it drags behind the car for the rest of the video. So from the 3 different tests I ran, you saw that the mean shift algorithm performed best in the actual tracking, which was kind of a surprise to me. I figured that the variance ratio algorithm would work better than at least as well as the mean shift, considering it's based on the mean shift algorithm. But in terms of efficiency and calculation, the one that requires the least work, the variance ratio one was actually the one that was able to get more calculations in per second. It was able to process almost 10 frames more per second than the other 2 algorithms. So basically, what can I conclude from all of this? Not too much. I need to do a lot more. I need to test a lot more video feeds, more tests that are closer to the application I envision, but it does give me a good first step into where I should look for object tracking algorithms and how to implement object tracking in the robot I hope to build. Thank you for your time, and I hope you enjoy your day.